A covalent bond is formed when the orbitals of two atoms overlap, and a pair of electrons occupy this overlap region. Just as with the case for atomic orbitals, the space formed by the overlapping orbitals can accommodate a maximum of 2 electrons, and furthermore, these electrons must have opposite spins. So, for example, spin up and spin down, or spin plus a half and spin minus a half. The greater the extent of orbital overlap, the stronger the bond. The extent of overlap depends on the shape and direction of the orbitals. In order for the orbitals to overlap, they must have the correct orientation and phase. Here the phases are represented by the colors red and blue. In the first example, we have molecular hydrogen, or H2, which is formed by the overlap of 2 atomic 1s orbitals. Next, we have the example of hydrogen fluoride, HF, which is formed by the overlap of the 1s atomic orbital on hydrogen and the 2p atomic orbital on fluorine. And notice that to form the bond, the 2 orbitals have to have the same phase. Finally, we have the example of fluorine, F2, which is formed by the overlap of 2 atomic p orbitals on each fluorine atom. And again, the orbitals are aligned so that the phases are the same, in this case, the 2 red phases. The greater the extent of overlap, the stronger the bond that is formed. It is important to note that the orbitals that are formed during bonding are different from the atomic orbitals that they originate from. This is because the atomic orbitals do not have the correct orientation for the molecular shapes and geometries that are experimentally observed. The atomic orbitals that we start with mix or hybridize when bonding occurs to form hybrid orbitals. The spatial orientation of these hybrid orbitals correspond with the observed molecular shapes. Some features of hybrid orbitals are 1. That the number of hybrid orbitals formed equals the number of atomic orbitals. 2. The type of hybrid orbitals formed varies with the types of atomic orbitals mixed. And we'll look into this further in greater depth during the following slides. Thirdly, the shape and orientation of a hybrid orbital maximizes the overlap with other atoms in the bond. In this example, we will look at beryllium chloride, or BeCl2. And here we have the Lewis structure for beryllium chloride, and we see that each of the chlorine atoms is bound to beryllium with a single bond. The next step is to take a look at the electron configuration for beryllium. And being in group 2 and looking at the periodic table, we can see that beryllium has the electron configuration He2s2, where He represents the core electrons and 2s2 represents the valence electrons. So we see that we have 2 valence electrons which are located in the 2s atomic orbital. Now, looking at those electrons in greater detail as an atomic orbital diagram, we can see that yes, indeed, those 2 valence electrons are located in the 2s atomic orbital, where one of the valence electrons is spin up and the other electron is spin down. Of course, in the case of beryllium, the 2p atomic orbitals are empty. Now, in order to create our hybrid orbitals, we will take one of the 2s atomic orbitals and one of the 2p atomic orbitals and combine or mix them to form our 2 sp hybrid orbitals. So we started with 2 atomic orbitals and created 2 hybrid orbitals, which are shown here. These are the sp hybridized orbitals. And you can see that both the shape and orientation of the atomic orbitals has changed when they were mixed and became sp hybrid orbitals. And in this case, our sp hybrid orbitals are located 180 degrees from one another. Of course, when we did the mixing or hybridization, we left 2 of the 2p atomic orbitals unhybridized, and so these 2 atomic orbitals remain unhybridized in our molecule. Now, when we're filling up our orbital diagram and placing our two valence electrons in the orbital diagram, we can see that the first electron goes in one sp hybrid orbital and the second valence electron goes in the other sp hybrid orbital. And you can see that in forming the bond in beryllium chloride, the chlorine atoms form one bond to beryllium with one sp hybrid orbital, and the other chlorine atom forms a bond with beryllium with the other sp hybrid orbital. This slide just illustrates the bonding in beryllium chloride, where we see that the bonds are formed between the 3p atomic orbitals on chlorine and the 2s atomic orbitals on beryllium. And the resulting compound, beryllium chloride, is shown here on the right, along with its Lewis structure.